The question I have is, could you do examples to illustrate the algebraic method of finding the resultant of forces? Let's start with the problem that was earlier solved using the parallelogram / triangle method, right? This is the answer we got. Let's see if we get the same answer by the algebraic method. The first step is to express each of the two force vectors in its component form. I have drawn these triangles that will help us find the projections of the force vectors in the x and y directions. Here is the triangle for the force vector F1, A, B, C. AC is the horizontal projection, in other words, the projection along the x-axis. Here is the arrow on that indicating its direction, and CB is the projection along the y-axis, and here is the arrow indicating its direction. To avoid crowding the figure too much, I took this triangle out and drawn this separately over here. We notice that this angle is 30 degrees and therefore this is 30. So we could either work with this angle or this angle, and this angle works out to be 60 degrees because we know this is 90 degrees and therefore this plus this must be 90. If this is 30, this must be 60 degrees. And similarly, here is the triangle to go with F2. Remember the definitions of sines and cosines, right? So if we have a right triangle like this, with these sides being A, B, and C, where C is the length of the hypotenuse, A is the length of the adjacent side to this angle, B is the length of the opposite side to this angle, then sine theta is defined as B over C, in other words, opposite side divided by the hypotenuse. And from that, we get this equation, right? B equals C times sine theta. In other words, you rearrange a little bit by cross-multiplying sine theta with C, we get an expression for B. So B is C times sine theta. And similarly, here's the definition of cosine theta. Cosine theta equals the adjacent length divided by the hypotenuse. And from that, we get this equation for A, right? Let's work on F1 first. So looking at this triangle, with respect to this angle 60 degrees, AC is the adjacent side, and therefore by this equation, AC equals 40 cosine 60, right? And CB happens to be the opposite side, and by this equation, CB would be equal to 40 sine 60, right? So 40 cosine 60 is the x component of F1, and 40 sine 60 is the y component of F1. Now the arrows, both of these arrows are aligned with the positive directions of the x and y axes respectively, and therefore they go in this equation as positive term. And of course you multiply each of these by their respective unit vectors. So little I is the unit vector in the x direction, little j is the unit vector in the y direction. So this is my vector representation of F1. In other words, F1 expressed in its component form. You simplify that using a calculator. Now with the help of this triangle, let's work on F2. The x component of F2 is AE, which is 60 cosine 40, and the arrow on that is in the same direction as the positive x direction, and therefore it goes in as a positive term here with the unit vector I. The y component of F2 is ED, which is 60 sine 40, but this time, of course, the arrow is in the opposite direction to the positive y direction. Therefore, that goes in as a negative term. Simplifying it, we get this. Now we add the 2 to find the resultant f. Remember what we do, right? The x component of the resultant f is the sum of the x component of f1 and f2. That will be 40 plus 45.96. And the y component of the resultant f is the sum of all the y components, which will be 34.64 minus 38.57. After simplifying, we get this. Next, on the basis of these numbers, we make a sketch of the resultant vector f. So we have a very large positive x component and a very small negative y component. And on the basis of this, here's my sketch. The vector f plots in the fourth quadrant. Now we go ahead and find the magnitude of f, which is square root of 65.96 squared plus 3.93 squared, which is 66.1 Newton. In order to define the direction, let's first go ahead and calculate this angle right here, alpha. Tan alpha would be equal to 3.93 divided by 65.96, right? And therefore, alpha is tan inverse of 3.93 divided by 65.96. Now we get 3.4 degrees for that. Theta here, which is the angle measured counterclockwise from the positive x-axis to the vector f, which works out to be 356.6 degrees. So you can either express the resultant as 66.1 Newton at minus 3.4 degrees, which is by measuring the angle in the clockwise direction from the positive x-axis, or 66.1 Newton at 356.6 degrees, which is by measuring the angle in the counterclockwise direction from the positive x-axis. Either way is acceptable. We also note that this result is the same as that we got from the triangle method. Let's do another example by the algebraic method. This time we have four different forces, F1, F2, F3 and F4. For each of these forces, the magnitude and the direction are given. When you have four different forces like here, the algebraic method works exactly the same way as if you have only two forces like in the earlier example. The first step is to find the components of each of the forces. Then the sum of the x components of the forces is the x component of the resultant force, and sum of the y components of the forces is the y component of the resultant force. In finding the components, at this stage, since we are still trying to get used to this method, it doesn't really hurt to physically draw these triangles for each of the vectors like we have done in the earlier example. Once you get used to this method, you could basically picture these triangles in your head and simply write down the components. Now remember, for each of the triangle, these arrows are as important as constructing the triangle itself, because the arrows are the ones that will tell us what sign to use with each component. Here is the component form of F1. The horizontal component is simply F1 cosine 50, and the vertical component is F1 sine 50. On the horizontal line, the arrow is pointing in the positive x direction. On the vertical line, the arrow is pointing in the positive y direction. Therefore, we have a positive sign in front of each of the two components. On F2, they did not give us any angles. Instead, they gave us these numbers that tell us the ratio between the vertical to horizontal sides of this little triangle. This is another way of representing the direction of a 2D vector. There are two methods for finding the components in this case. More precisely, there are two ways to understand the basis for finding the components here. In the first method, we use the principle of similar triangles. We note that this big triangle OAB and this little triangle CED are similar. Why similar? Because the corresponding sides are parallel to each other. Specifically, AB is parallel to ED, CD is parallel to OB, and of course OA and CE are parallel to each other because they are basically the same line, right? So the only difference between the two triangles is the length of corresponding sides. So when you have similar triangle, the ratios of the corresponding sides remain a constant. Say we are interested in finding this side, OB, right? You could either write OB over CD equals OA over CE, Or you could say OB over OA, like I have done here, equals CD over CE, CD over CE. Both of these are equivalent statements. Anyway, writing it this way, you rearrange this equation to express OB. So OB becomes equal to CD over CE times OA, where CD is 3, CE is 5, all right? OA is 180. So now you simplify that, you get 180 pounds out of that. Of course, in the original problem, they didn't give us the length of the hypotenuse of this small triangle, right? So we had to find it. So how much is that? That will be equal to square root of 3 squared plus 4 squared. So in this case, it works out to be 5. So that's how I got 5 here. All right, so similarly, to find the vertical side of this big triangle, I write this: BA over OA, BA over OA must be equal to DE over CE. And that, after simplifying, gives me 144 pounds for BA. So the x component of F2 is simply minus OB, because the arrow is pointing in the negative x direction, which works out to be minus 108 pounds. And the y component of F2 is simply equal to BA, which is 144 pounds. Another way to understand what we just did here is to use angles. We know that this angle right here and this angle, the angle of this little triangle, are equal to each other. So I call this as alpha. Now looking at the big triangle, we note that OB is simply OA cosine alpha, right? Now considering the little triangle, we see cosine alpha is nothing but 3 over 5. And therefore, OB is simply OA multiplied by 3 over 5. OA is 180, and therefore we get 188 pounds for OB, like we did over here. Following the same approach, we get a value of 144 pounds for BA, which is same as what we got in the earlier method. So just to sum it up, remember the following. You take this 180 pounds, right, and multiply that by 3 over 5, where 3 is the length of the horizontal side, in order to find the horizontal component of 180 pounds. And if you are interested in finding the vertical component, you take 180 pounds and multiply that by 4 over 5, where 4 is the vertical side of this little triangle. Here are my vector equations for F3 and F4, and I'm pretty sure you can follow the details easily. So here is the resultant. We sum up the x component of each of the 4 forces here and put that along with the unit vector I, and we sum up the y component of each of the 4 forces here and put that along with the unit vector j. After simplifying, we have this for the resultant vector. Now let's go ahead and present this in the proper way. So what do? Well, on the basis of these numbers, we make a sketch. We have a negative x component and a positive y component for the resultant, and therefore the resultant sketches in the second quadrant, like in this picture. Using the Pythagorean theorem, the magnitude of f, which is the length of the hypotenuse of this little triangle, right, equals square root of 50.94 squared plus 185.8 squared. So we get a value of 192.7, and of course put the unit of the force at this point. The unit is pounds, right? And therefore the resultant is 192.7 pounds. To define the direction, let's first go ahead and find this angle alpha. Alpha is tan inverse of the opposite side divided by the adjacent side of the triangle with respect to that angle alpha. So that's 185.8 divided by 50.94, and we get a value of 74.7 degrees for alpha. And to define the direction in the standard way, which is by using an angle measured counterclockwise from the positive x-axis. Let's go ahead and find this angle, theta. Theta is 180 minus alpha, right? So we get a value of 105.3 degrees for that. And therefore, the proper way to present the result is that the resultant is 192.7 pounds at 105.3 degrees.